Okay, so you've brought us a sequence of numbers today,
We have.
and it's called A000003. And looking at it, I gotta say it's mostly ones and twos. Is there something like more to this?
Yeah, so this sequence has kind of baffled mathematicians for a long time because there's no easy way, there's no formula to figure out what the next term is going to be.
Really?
Yeah.
Yeah, after all this time.
Yeah, they haven't figured out a formula yet.
Okay, so what's the sequence all about then?
So this all revolves around something called binary quadratic forms.
Okay.
And it's a little easier to understand with an example. Imagine you're building a fence, right?
Okay.
A rectangular fence.
I'm with you.
And you have a set amount of fencing material.
So I can make it like long and thin or more like a square.
Exactly.
Okay.
Now those different rectangle shapes that you can build with that same amount of fencing, those are your different forms. And this A000003 sequence is basically counting up how many different fence designs you can make as you adjust how much fencing that you have.
Okay, so it's not about the fences themselves, but like the potential for different shapes.
The potential, exactly.
Okay.
And so imagine if instead of simple rectangles, we're talking about mathematical expressions, equations that describe shapes. And as those shapes get more and more complex, then so do the equations.
Right.
And so this sequence is kind of giving us a glimpse into this hidden world of increasingly more complex mathematical structures.
Wow. So this isn't just some random sequence of numbers. It's like describing something fundamental about how math itself is structured.
Precisely.
Oh,
And it gets even deeper than that. This sequence doesn't just hang out in the realm of basic shapes and equations. It pops up in some pretty high-level math, too.
really? Like what? So last we left off, you were about to tell me about this sequence popping up in some really advanced math.
Yeah.
Okay, hit me with it.
So one of the areas that it pops up is something called elliptic integrals.
Okay.
And before you start thinking too hard about that, just think about like an ellipse,
Okay.
like kind of like stretched out circle shape.
Like the path the planet makes around the sun, right?
Exactly. Yeah, exactly. And so if you want to figure out like how long is that elliptical path,
Mm-hmm.
it's not as easy as just like, figuring out the circumference of a circle.
Right, right.
And that's where these elliptic integrals come in.
Okay.
They're like these kind of special tools for measuring those kinds of curvy distances.
So where does our sequence fit into all of this? We've got ellipses, we've got these integrals. Like, where is the connection?
Yeah, so this is where it gets really interesting.
Okay.
So remember we were talking about those like increasingly complex shapes and equations.
Mm.
It turns out there's this connection between this sequence, I know 000003, and the complexity of some of the equations that pop up when you're dealing with these elliptic integrals.
Wow. So it's like the sequence is telling us something about the underlying math. Like, used to understand those elliptical paths. That's pretty cool.
Yeah, and it gets even weirder.
Oh.
There's another connection that's even more out there. We're going pretty abstract here, but this A000003 sequence also has ties to something called Klein's J-Invariant.
Okay, I'm gonna be honest with you. That sounds a little beyond me, but I'm all ears.
Yeah, so basically, I mean, think of it this way. Klein's J-Invariant is like this really important tool in a very specific branch of math that deals with these things called complex numbers
Okay.
and all sorts of like really strange multidimensional shapes.
Mm-hmm.
And somehow our sequence with just its ones and twos, it manages to weave its way to that world too.
So it's like a common thread between these different areas of math.
Yeah, it's a weird connecting thread between all these different things, and that's part of what makes it so interesting to mathematicians.
So, okay, my brain is trying to keep up with all of this. This is a lot.
Yeah.
But I do have to ask, like, this is all fascinating from like a theoretical point of view, but what about the real world? Like, does this sequence actually have any practical uses? So this sequence, A000003, it's connected to ellipses, to this Klein's J-invariant, but last we left off, you were about to tell me about how it has like real world applications.
Right. Yeah. So as abstract as it seems, this sequence, it actually has implications for things like online security, believe it or not.
Wait, really? How does this sequence have anything to do with like keeping my online shopping safe?
Well, a lot of online security, it relies on cryptography, which is essentially like the art of sending secret messages that only the intended recipient can can decipher.
Right.
And a lot of cryptography is based on prime numbers.
Okay.
You know, those numbers you can only divide by one of themselves.
Yeah, I remember those from way back.
Right. So figuring out if a really, really big number is prime and finding those big prime numbers to begin with, it's really hard, even for computers, like really powerful computers.
Okay.
And it turns out that this sequence we've been talking about can actually help mathematicians develop more efficient algorithms for tackling these prime number problems.
Wow. So it's like this sequence which describes these complex shapes and structures in math.
It's also giving us tools to like solve real world problems in cryptography.
That's so cool.
And here's the really interesting thing.
Okay.
Even though we've uncovered all these amazing connections, right, and these applications for A000003, there's still a fundamental mystery surrounding it.
A mystery? What do you mean?
No one has found what we call a closed form formula for it.
A closed form formula? What is that?
So basically, it would be an equation where you could plug in any number. Let's say you want the 100th term. You plug in 100.
Okay.
And it would just spit out that 100th number in the sequence directly.
Oh, so it's like a shortcut.
Exactly, yeah, like a shortcut.
You're telling me we don't have a shortcut for this?
We don't know, and mathematicians have been trying to find one for a really long time.
Wow.
And it remains one of those really like tantalizing unsolved problems in math.
It's kind of amazing to think that even though we can see how this sequence connects to all these different areas, there's still that like missing piece.
Yeah, and I think that's kind of what makes this sequence so captivating, you know?
Yeah.
It's a reminder that even in a field like math, where we feel like we're uncovering these absolute truths, there's still mysteries, you know? Still things we don't know.
Well, that's pretty amazing to think about, and I really enjoyed this deep dive. This was a really interesting sequence.
Oh, good. I'm glad.
And that's it for today, so until next time.